Welcome to this video. My name is Mark Scythian. The date today is July 16, 2024. This presentation or lecture is going to focus on the US and metric systems of measure. The metric system is the completion of the unfinished English Kelvin-Rankine-Newton-Watt system of measure incepted from the ancient Egyptian, Mesopotamian, Hindu systems of enumeration, thus completed in the early 20th century or early 1900s, when the inverse of the speed of light yielded 3.28 feet per meter, relevant to the atomic and subatomic measurement accuracies. Therefore, the metric system is the most scientifically accurate, easiest, and most universally consistent system of measure, provided one is familiar with both the US imperial and metric systems of measure. So scientific modeling, this is the metric system, or production, research and development. The sales and marketing side is the metric system converted to US units of measure on the consumption or consumer side. So we have 4.45 newtons of force, that's 1 pound force. Now when dealing with kilograms of mass, this is equal to 2.2 pounds mass. Gravitational acceleration on Earth, little g, is 9.81 meters per second squared, which is equivalent to 32.2 feet per second squared. Force weight is mass times gravity, so we have a constant mass value throughout the universe. It is the number of atoms and molecules or molar mass of a substance, liquid, solids, and gases especially. Now if we multiply the constant of mass times a gravity on some sort of a celestial body, it could be the Earth or the Moon or Mars or Jupiter, etc., then we have a force weight. So weight itself is the product of mass times gravity. Gravity itself is actually an acceleration consistent with the mass radius of a celestial body, i.e. a planet. So 1 Newton of force in the metric system is equal to 0.102 kilograms times gravity, or an acceleration constant of 9.81 meters per second squared, hence F equals mg, and that gravity is a magnitude and direction, or a vector, perfectly straight down towards the center of, in this case, the celestial body being Earth, its center. 1 Newton meter is a unit of work, synonymous with a joule. So force times distance is the concept of work. In the metric system, that is the joule or the Newton meter. This is equivalent to 0.737 foot-pounds of work in the US system of measure. So now when we divide the work, or the force times distance, into time, we now have the potential energy as a function of work converting into a kinetic energy over the function of time. So 1 joule per second is 1 watt, which is synonymous with 0.737 foot-pounds per second, a unit of power. So if we divide the work into time, we get power. So hence the completion of the Old English system into the metric system. So it is not very accurate to describe the metric and US systems of measure as alien, disconnected, non-related systems, when they're actually a continuum from the Old English system to a totality or a final measurement conclusion into the metric system. So for example, if we're at a foot-pound, we also have 1.36 joules is equivalent to 1 foot-pound. with respect to work, and so that translates to 0.737 foot-pounds per second, or 1 joule per second, or 1 watt. So again, if we were to take 746 of those watts, we would have the horsepower in the United States and the recent English migrations, even in some respects in Australia, and of course in Scotland they kept the Old English system for the longest time, but even they converted over to the metric system. Now if we move on to volume, 1 US gallon, we must specify US gallon as a volume of liquid substance is 3.78 liters, or 3780 cc's, or 3780 milliliters. So a cc and a milliliter are synonymous. Now we also have the US gallon volume measurement with respect to dry or gaseous gallons. So if we're talking about the volume of a gas and we were measuring it in a US gallon volume metric, we would then have an increase by 16% to 4.4 liters is 1 dry US gallon, or 4,400 cc's, 4,400 milliliters. We also have the cubic inch, which is equal to 16.387 cubic centimeters, and of course 1 cubic centimeter cc is 0.06 cubic inches. So now we have in the U.S. Not necessarily the Old English system, but the U.S. imperial system, its own system. Well, say towards the end of the 1800s, or about the time the Old English system and the U.S. imperial system kind of were one and the same, but kind of different in their own way. So one may question, is there any absolute mass values in the U.S. system of measure? And actually the answer is yes. It is known as the slug weight. And notice it is 32.2 pounds is 1 slug. This is an absolute weight, and of course it correlates with the 32.2 feet per second squared gravitational acceleration measured in the U.S. system of imperial units. So 1 pound mass is also equal to 0.031 slugs. And then of course we have the grain, which is very common in ballistics, either for the projectile or the smokeless powder, and that's measured in grain. So just 1 grain is simply 64.8 milligrams, in equivalent to the metric system. Next we have dynamic force, and again this is not the same as the force weight. We would call that static force. An object resting on a table is still the mass times the gravitational acceleration. So mass times acceleration is force, and if we replace the little a with a little g, we get the mass times gravity, and this is then synonymous with some type of force, and in this case that would be a static force. But when we relate dynamic force, as in propulsive force, thrust pushing an airplane, or somebody pushing a table horizontally, that horizontal force is our force that's going to accelerate or move something, we'll put it that way. But it's very common to have a horizontal force vector, but it could also be lift. It also could be counter force or drag force, opposite direction of the normal direction of motion. So this is the dynamic force, and again this is the mass times acceleration, but the acceleration is not the speed, but it is the change in the speed. The speed is the distance divided into time, but then if we divide that ratio into time once more, then the acceleration becomes distance divided by time squared. And as you can see, we have feet per second squared for the units, we have meters per second squared for the acceleration unit, so that is some distance divided into some type of a time period squared. So if we were going to convert this into the metric system, you would simply just use the feet, divide it by 3.28, and then divide it into the amount of time the acceleration or change in speed took place. So in seconds, that quantity in seconds squared. So d over t squared acceleration. And of course, if we want to bring that back from meters per second squared to feet per second squared, we can just multiply the meters per second squared acceleration times 3.28. So here we have 1 meter is 3.28 feet, 1 inch is 25.4 millimeters, 1 inch is also equal to 2.54 centimeters, 1 foot is 0.3 meters, 1 millimeter is 0.039 inches is 1 millimeter, and 0.39 inches is 1 centimeter. So next we have pressure. 1 psi pressure is also equivalent to 6894.76 pascals. So the difference between the pascal and the psi for pressure is that the whole concept of pressure is some force divided into area. So if we were to apply a force and then decrease the area, or have a certain amount of force over less area, then the pressure will go up, right? So if we had more contact area with a constant force, then the pressure would decrease. So it's just force divided by area. And so if we measured in the metric system Newton's force, that is the kilogram times meters per second squared of acceleration, as measured in the newtons, if we were to apply Newton's force divided into a square meter of area, then we have 1 pascal. And of course, if we apply 1 pound of force per square inch, we have 1 psi. So other metric equivalents, or cross US and metric equivalents, of course, we have standard atmospheric pressure at mean sea level, 14.7 psi. This is equal to 101,353 pascals of pressure, and there are 100,000 pascals to a bar. So 101,353 divided into 100,000 is 1.01 bar. This is standard atmospheric pressure at mean sea level, 1.01 bar. And in inches of mercury, regarding the US system, is 29.92 inches of mercury. That is the 14.7 psi atmospheric pressure, which is equal to 1 torricelli, or 760 millimeters mercury. So that's very common in blood pressure readings, the millimeters of mercury. So if you were just curious what that was in psi, let's say you had a systolic upper number of 130 and a lower diastolic number of 70, you could just take the 130 and divide it into 760 and then multiply it times 14.7, and you get the psi equivalent. And of course, you could do the same for the lower number, the diastolic. And then, of course, if you look at millibar, that is a bar divided into 1,000. So again, if we were to divide 101,353 pascals, or 100,000 plus 1,353 pascals, or 1.01 bar, we could get also 1013 millibar as equal to 14.7 psi, mean sea level, standard atmospheric pressure as well. Let's see here, we have 1 cubic foot of volume is 7.5 US gallons. That's US gallons liquid. And if it was gaseous, then it would be 8.7 US gallons dry to 1 cubic foot of volume. And this is with respect to liquids mainly. But if you're dealing with a dry cubic foot of gas, then it is 0.156 cubic feet. Dry volume is 1 US dry gallon. 1 mile, 5280 feet. This is a distance, once again, but in different parameters and units. So a mile just means 5280 feet, which is equal to equivalent to 1609.75 meters. So about 1610 meters, and that's 1.6 or 1.61 kilometers. So the miles per hour again is the ratio of the kilometers per hour times 1.6, and vice versa. So if you're wanting to know the miles per hour from kilometers per hour, then it would just be dividing it, kilometers per hour, into 1.6. So in the US system of measure, we have 15 miles per hour as an increment. This is equal to 22 feet per second, or 6.7 meters per second. So if you went up to 45 miles per hour, then it would go to 66 feet per second, and then 3 times 6.7. So we'll just round it close to like 20 meters per second. 1 nautical mile or a knot is 15% longer than a normal or statute mile. So 72 feet is 1 nautical mile. This is 1851.2 meters or 1.85 kilometers. Now we have 2 different temperature scales. We have the relative temperature scale, which is not an absolute. It's not from an absolute zero temperature value. So just to get an idea of what absolute zero is, it's theoretically highly specialized. It is possible, but this is where we start to get a very quantum reaction at zero molecular activity, and not even outer space is absolute zero in temperature. So technologically creating absolute zero environment has been very close, like 0.7 to absolute zero. So that would be almost minus 460 below zero, and almost minus 460 below zero Fahrenheit, and almost negative 273 below zero Celsius. So when you stop all molecular activity, even neutronic or neutrino energy, things like having a simultaneous position occur. And this is a little bit more relative to the zeroth law of thermodynamics. And so, again, we have an absolute versus a relative temperature. So if you're using Fahrenheit or Celsius, these are relative temperature values. And they're taking off a relativity, not a absolute from zero. So if you're dealing with converting degrees Fahrenheit relative temperature to degrees Celsius, you just take the Fahrenheit temperature, you subtract 32, and then multiply it times the fraction of 5/9, or you could multiply that difference times 5 and then divide it into 9. Now to convert from Celsius to Fahrenheit, you just do the inverse function of that. So you would just take the Celsius degrees and multiply it times 9, divide it by 5, and then add 32. Or you could take the Celsius value and multiply it times the whole fraction quantity of 9/5 and then add 32. And so then when you get to Celsius and you want to convert this into the absolute temperature, it can only be Celsius to Kelvin in the metric system. So that is Celsius plus 273 to yield the absolute temperature in Kelvin, metric value, absolute temperature. And then with the Rankine absolute temperature scale, that's only relevant to the degrees Fahrenheit plus 460, and that will yield the degrees Rankine absolute temperature. So again, if we were to go to absolute zero, it would be minus 460 below zero Fahrenheit or minus 273 below zero Celsius. So we have quantities of heat, measurements of heat, not necessarily temperature or kinetic molecular activity, but we're talking about, for example, a potential energy of heat, let's say in fuel or food, or something that could be converted into heat or ignited or consumed from a substance into a heat source. That's the potentials of the kinetic energy. We have the British thermal unit, 1 BTU, and this is the equivalent heat required to raise 1 pound of water by 1 degree Fahrenheit. This is also synonymous with 252 calories of heat. But remember, we don't have a time metric, as in BTU per second or calories per second. We only have the BTU and the calorie, so those are potential energy values. And so, of course, it would really be a BTU per pound or a calorie per gram would be the absolute or the most accurate potential energy measurement. But in a general sense, a one-dimensional sense, the BTU is also synonymous with 252 calories. So if we release 1 BTU per second in the form of heat, any type of heat, it could be combustion of fuel, it could be electric heat, it could be any type of heat that if you were to transfer it into a pound of water, and the temperature would increase at a rate of 1 degree Fahrenheit per 1 second, then that is 1,056 watts of power, at least on the input side. So you don't have 100% thermal transfer efficiency. You do have about a 20, 30, 40% loss depending on the material. So the input energy, or input power in this case, at 1 B2 per second is 1056 watts. But the output, what you actually get into the water or into the machine or the device, that definitely will not be 100% efficient. So definitely be less than 1056 watts at 1 B2 per second. And so what correlates to the calorie per second, 1 calorie per second is 4.184 joules per second, or 4.184 watts of power. So that power could be any type of equivalent. It could have came from electricity and then went to a heating element and then became heat, electrical to thermal power. It could have been from any other power source. It could have been even sound power, refracting against the material, and then the efficiency losses become heat as well. I mean, it could have been anything, but it's just generally 1 calorie per second, or the amount of heat required to raise 1 gram of water by 1 degree Celsius every second is equal to 4.184 watts. And then, of course, 1 calorie in the one-dimensional conversion is synonymous with 0.004 BTU. So here we have a cubic foot, we get its cube root, we get 1 foot linear, we divide that into 3.28, we cube it, and now we have 0.0283 cubic meters. So what does that say? 1 cubic foot is also equal to 0.0283 cubic meters. That's volume, US to metric conversion. Again, we could take the pound per cubic foot, let's say air density, and convert it to a kilogram per cubic meter value. So air density tends to be like, 0.074 pounds per cubic foot at like standard conditions, like 60 degrees Fahrenheit, near or at sea level, etc. But imagine a whole pound per cubic foot. So that's a pretty heavy gas. So, it would be a very heavy gas, or could just be a 1 pound per cubic foot metric. It'd just be a conversion factor metric, right? So if we just wanted to see what that is in kilograms per cubic meter, we could take the 1 pound, divide it into 2.2 to get the kilograms, and then we could just use the cube root of 1 divided into 3.28. That quantity cubed would become 0.0283. And when we get these difference, it translates to 16.06 kilograms per cubic meter. So if you were to actually use that correlation, let's say we want 1 over 1606 to go from kg per cubic meter to pounds per cubic foot, you could do that. Or you could flip it around and just go 16.06 over 1. And so based on how you flip that around in the ratio, you could actually have that as a conversion factor. And so then next is the pound mass, of course, is 1 divided into 2.2, or 0.45 kilograms. So 1 pound mass is 0.45 kilograms. So if we focus just on a gallon of water, a U.S. liquid gallon of water, a U.S. liquid gallon volume, in this case water, a gallon of water, that would be 8.3 pounds in the pounds mass. So we'll just call it the weight, even though that is really like pounds force weight. So it's 8.3 pounds is 1 U.S. gallon of water, and that's equivalent to 3.78 liters, or 128 volume ounces, which is also equal to 3.77 kilograms, and 132.8 mass ounces, or at least weight ounces, we'll say this, and because there's 16 weight ounces to a pound. So 16 times 8.3, 132.8 mass ounces, and that in a volume is equivalent to 3780 cc's, or 230.67 cubic inches, or 0.134 cubic feet. So all of these, when there's more repetition with these conversions and you're looking at it every day, becomes super simple to work with the metric system and even look at a gallon of gas and say that's 3.78 liters. We're close to like 4 liters. And then we have the quart, 1/4 of a gallon. So it's very close. It's just that when the inverse of the light second became certified fact as 3.28 meters, we could take that distance, one-dimensional distance, and now square it into area and then cube it into volume. So this is when things like the quart became the liter. We're very close to 4 liters per US gallon, but we know 4 quarts is a US gallon. And so I'm talking about the scientific accuracy, these little approximations. Now we have the accuracy and the precision. So when there is too much accuracy or too much a non-tolerant, a value that is so precise there's no tolerance, and that's not reality. Reality, everything's kind of expanding, contracting, going up and down a little bit. So you have a precise value, a snapshot in time, and that might be very relevant to 2, 3, 4 significant digits into the decimals. But then when you're doing actual real world specifications, the tolerances are required. So that's where the precision is not necessarily the correct value, unless it might be for incremental testing at a specific time. But the practicality of a specification is not with precision, but with accuracy. So that's where the degree of freedom for both the precision and the accuracy is far more simplistic and consistent more than anything when using the metric system. So really it isn't as if you're abandoning the US for the metric system. You kind of actually have the upper hand if you could just continue the continuum of the US English system into the metric system. That's a huge advantage, because it would be ideal to just make computations using both the US and the metric together. So again, we have another value for density of water, 62.4 pounds per cubic foot. This is synonymous with 1028 kilograms per cubic meter volume. That's the density of water in a metric system. For practicality, in the kilograms per cubic meter rather than the grams per cubic centimeter. So then we have the foot-pound torque. Everybody's familiar with the foot-pound torque with engines and the foot-pounds torque at a certain RPM, and of course the ratchets and the torque wrenches, etc. And so one, just like we had 0.737 foot-pounds per second to a joule or a Newton meter, we can use that standard or metric or equivalency with the foot-pounds torque or torque moment. So 1 foot-pound torque is also equal to 1.36 Newton meters, because we know that there's 1.36 joules or Newton meters to a foot-pound. So whether we're doing foot-pound for work or we're doing it on an angular vector for rotation moments and torque, we still have a similar standard here, but on a rotational or orbital vector, we'll put it like that. So 1 Newton meter of torque is 0.737 foot-pounds torque, and 1 foot-pound torque is equal to 1.36 Newton meters torque. So you often see that in the engines and motor torque specifications. They'll put the foot-pounds and then they'll also put the Newton meters, and so you have an inverse function of 1.36 versus 0.737. And everyone's familiar with horsepower, but that is also equal to 746 watts or 746 joules per second. 1 joule per second is 1 watt of power, and that is synonymous with 550 foot-pounds per second. So look at it. If you were to divide the 550 into 746, yep, you get the 0.737. And if you were to divide the 746 into 550, you get the 1.36. So there you have it. That is the US English system of measure to completion into the metric system. So the metric system is the completion of the U.S. English / U.S. imperial system, as both the Old English and the U.S. English system kind of worked in parallel throughout the late 1800s into the mid 1800s into the late 1800s, and then they kind of split into U.S. imperial and then Old English, or we'll just call it the English, and then the English went away and became the metric system. Okay, so the metric system is the completion of the U.S. English / U.S. imperial system, or systems of measure, to absolute accuracy. Not even England / UK uses the Old English system of measurement, except for the United States, Myanmar, and Liberia. Thank you for watching this lecture / presentation, and have a great day.